Remember, a key prediction of general relativity is that it fails at some point, that there are singularities. So it's a theory that predicts its own downfall. But so far, we only know about that because we have solutions which have singularities, such as the Schwarzschild solution. But does that really mean that in realistic scenarios, in actual space-time, we should expect singularities? The Schwarzschild solution is the outcome of the formation of a black hole that just comes into existence and exists forever. But realistically, there was a stellar collapse and symmetry is not perfect. It's not clear that in a non-symmetric collapse, you actually get a solution that has a singularity in it. In classical physics, we would not. In Newtonian collapse would not. If it's completely symmetric, then sure, everything would just collapse into a point. But if there's a bit of non-symmetry in there, then the angular momentum would have to be preserved and everything would collapse but spin out again. So how is that in general relativity? Are there singularities really? And if there are singularities, then probably they need to be overcome by quantum theory. So the plan is we continue to study these connected notions of causality, horizons, and singularities. The next concept among the horizons to come up is Cauchy horizons, but then we will also look again at event horizons and trapped horizons, and if we have the time, killing horizons. There's a whole zoo of them out there, and it's good to get an overview. Yes, and then singularity theorems, to see if there are really singularities predicted by general relativity in generic situations without symmetry. Okay, in what we will do now, we will always assume that the space-time is causal and stably causal, in the sense that we discussed in the previous lecture. Then in extendable paths, if you remember, they don't have to be geodesics, just paths. In extendable paths, either go all the way to infinity, or they end in a singularity. And that's the case that we'll be interested in. So our method of the detection of a singularity is going to be related to the extendability of a path. And that will lead us to, so the study of inextendable curves will lead us to the concepts of Cauchy horizon and the concept of global hyperbolicity. Remember, we considered the set I plus that, or also J plus, that can be reached from a set of events S. It is the set, let's say this is J, I should have drawn this a little deeper there. J plus is the set of all events that can be reached by whatever means from another set of events S. So it's the set of events that can be influenced by the events on the set S, either through radiation or through traveling matter. So this is, so to speak, the zone of influence of S. Now let us consider the set of points that can only be reached from S. This is the set of events that will depend only on what happened on S before. So let's assume that S is a set of events in a manifold which is closed and achronal. Remember, achronal means that there is no way that any matter, any chronometer for that matter, any piece of matter could travel between any two events in S. Okay, so the events in S are space-like or light-like to another, but they cannot be time-like to another. So we consider one of those sets, and then we define the future domain of dependence of that set of events denoted by D plus, as the set of all those events in the manifold which are such that every past inextendable causal curve through that point intersects our set of events S. So here's a picture. It's probably much easier to see in a picture. Here is our set S, set of events S that are achronal. Think of a space-like hypersurface, or a piece of a space-like hypersurface. Then imagine that this is the manifold, it's total manifold, that's just this little piece of space-like hypersurface. And imagine that there's a singularity in there. Okay, so let's look at an event in here. The event that I'm pointing to now is clearly in D+. Because every past inextendable causal curve through that point P, every curve inside the past light cone that's inextendable will hit eventually that curve, will eventually intersect S. And the physical intuition for why we consider that set of points is that all those points are completely determined by what happened on S. If you want to know what happened at that point in space and time, you need not know what happened over there, because it's too far away. Even light could not have traveled to there in time. So this S is all you need to know. If you have initial conditions on just S, you should be able to predict what happened anywhere in here. But look at the presence of a singularity. If there's a singularity, then it casts a shadow in the sense of this definition here. See, consider this point Q here, which is outside the future domain of dependence of S. Why is it outside? Well, it's because you can write down a inextendable causal curve through P, or through Q, an inextendable causal curve. It's inextendable because there's a singularity here, which goes to the past, and it's causal. Remember, causal means at or below the speed of light. So we can write down a path which is inextendable but does not meet S. Okay, so it has to be excluded, just like you point out here. You can write down paths that are inextendable, go to the past, and don't meet S. So they are not in D plus of S. So all those points in here, in the shadow of that singularity, are not in D plus, because while they may be influenced by what is going on in S, they are not completely influenced in the sense that all past inextendable curves hit S. And remember, in all those diagrams, there's always space in this direction, time in the upwards direction. And similarly, we can define the past domain of dependence of an achronal set S. The past domain of dependence, D minus, is the set of all those events in the space-time which have the property that every future inextendable causal curve through P will eventually intersect S. So this is the set of all those events which will affect S, but only S. They cannot affect anything that's to the left or to the right of S, because the light cone is not wide enough. And then we define the full domain of dependence of S as the union of the future and the past domain of dependence of S. And this leads to the definition of the Cauchy horizon. Let us consider the set of the latest events that can be affected only by S. So if you have initial conditions on S, the overall idea is this. If you have initial conditions on a piece of a space-like hypersurface, S, how far can you predict? And that's what the Cauchy horizon is indicating. Okay, so the future Cauchy horizon of S, which we will denote by H plus of S, H for horizon, is the completion of D plus of S. It's the completion of the future domain of dependence, and then we subtract the past of it. So we take the future domain of dependence, okay, and then we subtract, complete it, and then we subtract the past of it so that we are just left with the boundary of it, okay? And that's as far as the predictions go if you have initial conditions here. If you have initial conditions here, then you can predict completely everything that's in here up to this boundary, and that's the future Cauchy horizon.
Is the singularity included in that?
No, no, it cannot. It's not part of the. Yeah, it's not a point. That's right. That's why I drew it as a whole. And then similarly, the past Cauchy horizon of S is the set of earliest events that can affect only S, but that are too close to S. You see events down here, for example, an event here, it has a forward light cone like this, so it can only affect events on S, but it cannot affect events outside, right? So events in here are all in the past domain of dependence, and the boundary of the past domain of dependence is then the past Cauchy horizon. So the past Cauchy horizon is obtained by closing the past domain of dependence and then subtracting its interior, namely its causal future, its chronological future. The full Cauchy horizon of S is then this boundary, the upper one, plus the lower one. I mean, the lower one might also suffer from some singularities, but just generally it's both boundaries. It's the boundary of the full domain of dependence. Now one can prove that the full Cauchy horizon of S is simply the boundary of the domain of dependence, just the boundary of the full domain of dependence. Now we come to the key concept of a Cauchy surface. A closed achronal set S is called a Cauchy surface if its full Cauchy horizon vanishes, if it doesn't have a Cauchy horizon. Right? So a Cauchy surface is an achronal set. Think of a space-like submanifold. And it has, in general, a future and a past Cauchy horizon. If it doesn't, then it's called a Cauchy surface. And if it doesn't have such a horizon, what it means is that you can predict everything from it. You can predict and postdate everything if you just know what is happening on the Cauchy surface. And mathematically, this is to say that the full Cauchy horizon is the empty set, because it's really out there at infinity, but that's not a point. It's not a set of points. The boundary of the domain of dependence is empty, and the domain of dependence itself is the entire manifold. They all mean the same thing. This definition follows the textbook by Wald. There are slight variations to how these things are formulated, but I think they are equivalent. If you look in the textbook by Hawking and Ellis, Gerroch and others, they will express things a little differently, use a little different terminology and notation, but essentially it's the same. But it's a bit of a jungle there with the notation. A few remarks. Cauchy surfaces are important because if the conditions on a Cauchy surface are known, then everything on the manifold can be predicted and retrodicted, at least in principle. It still depends on what the equations of motion are. They might screw it up. But in principle, it is possible because there are causal curves everywhere to the future and to the past from a Cauchy surface. You might wonder, does it ever happen when that is not the case? Well, for example, in anti-de Sitter space, there are no Cauchy surfaces. Now, since a Cauchy surface is achronal, remember, achronal means that no two events in a Cauchy surface are time-like to each other. A Cauchy surface can be viewed as an instant in time. It's like a moment in time. We've chosen a space-like hypersurface that indicates some instant in time. And the term surface is motivated by the theorem that every Cauchy surface, let's call it sigma, is a three-dimensional continuous submanifold of the space-time in 3 + 1 dimensional space-time. Then the term global hyperbolicity comes up a lot, and what it really means is simply that the manifold possesses a Cauchy surface. That's in one-to-one correspondence, just a definition. This notion will come up later on for the purpose of cosmological singularity theorems. We will have to make some assumptions about space-time and about the matter in the space-time, and global hyperbolicity will be one of those assumptions. Now remember that a Cauchy surface can be viewed as an instant in time. Indeed, there's a proposition, and it says that if a space-time is globally hyperbolic, so it has a Cauchy surface, then there exists a global time function f, so that every surface of constant f is a Cauchy surface. And if such a global time function exists, then the manifold is also stably and therefore strongly causal. Remember, we had that, we talked about that as well in the previous lecture, namely that if you have a time-like non-vanishing vector field that's a gradient field, then you have stable causality, and the scalar function of which the time-like vector field is the gradient is giving you a global time function like that. Okay, now our overall plan was to study inextendable geodesics in order to detect singularities. Now, or in principle, inextendable paths as well. Now, how to identify these geodesics which are inextendable because they end in a singularity of the manifold? See, some geodesics could be non-extendable for a different reason. For example, in the picture that I drew before, I just punched a hole into the manifold. Now, technically that's a singularity, but it's not a singularity of an interesting kind, because we could fix it easily. We could just continue the manifold, patch up that hole, and we would end up with a differentiable manifold, Lorentzian manifold, no problem. So there was no reason for that, singularity. We want to avoid that situation where we get inconsequential singularities, where we detect inconsequential singularities. So we adopted the definition that a space-time M is inextendable, and now this is not a statement about geodesics, it's a statement about space-times. We say that a space-time is inextendable if it is not isometric to a proper subset of another space-time that is larger. So we will always assume that our space-time is as far extended as possible, so those trivial holes are assumed always to be patched. And then we are only left with interesting singularities. And there are different kinds of those interesting singularities, but the trivial ones we just eliminated. Now, an important definition is this. A geodesic which is inextendable, but possesses a finite range of its affine parameter, is incomplete. You see, if a geodesic is inextendable, but it has an infinite range of its affine parameter, then it could just be running off to infinity. We are looking for geodesics that run at a finite point, at a finite location into a singularity. And so what we'll be looking for is geodesics that are incomplete. So they cannot be extended, but their affine parameter is only running to a finite value. Yep.
Something like take anything that has, like take 10 to make any finite value to be able to let it go to infinity.
Well, that's right. Yes, yes.
It wouldn't be a geodesic then. Geodesics have to go at certain speeds.
No.
At a constant speed.
You can reparameterize it. But you see here, but the question is, can you write down a geodesic such that the parameter runs only a finite number of values and cannot extend it? Right. So, well, let's see how it plays out. Okay, and then we say that a manifold, a space-time, possesses a singularity. That's the definition of singularity that we will adopt if it possesses an incomplete geodesic. Now, generally, if it possesses one incomplete geodesic, it will possess infinitely many of them, but we'll just need one to identify the presence of a singularity. Depending on whether that incomplete geodesic is time-like, light-like, or space-like, remember, we are not restricting attention to geodesics that could actually be traveled. You can also look at space-like geodesics. Depending on the nature of the geodesic that detects a singularity, we will then speak correspondingly of a singularity that is time-like or light-like or space-like. Now, the space-like ones are not considered to be of importance, but they may, who knows? Now, when going along an incomplete geodesic towards a singularity, then three things can happen. And we've already excluded here the trivial case where we just punched a hole into the manifold. What can happen is that a scalar, this is going to be a classification of singularities, right? So first possibility is that a scalar constructed from the curvature tensor diverges. So for example, the curvature scalar, the Ricci scalar, might be divergent as you travel along that geodesic. And then you can't extend it beyond where the singularity of R is. It could also be that higher order scalars that you can form from the Ricci tensor or the Riemann curvature tensor are divergent. In this case, we say that a scalar that we have a scalar curvature singularity. Right? So if when you travel along a geodesic, a scalar that you can build from the curvature tensor is diverging, then we say that this is a scalar curvature singularity. And it is, in principle, it is possible that this is divergent and that is not, and vice versa. So there are different kinds of scalar curvature singularities. It could also be that none of those scalars diverges, but that something tensorial about the curvature is divergent. I mean, just to highlight what the issue here is, remember that curvature can be, the Riemann curvature tensor can be decomposed into a Ricci component and a Weil component. The Weil component having to do with gravitational waves and things like that. And the Ricci component is directly related to energy and matter. And clearly, if we're only looking for divergences in the Ricci curvature, we may be overlooking divergences in the Weyl curvature, which in principle might also happen. So another possibility then having scalar curvature divergent is that in a parallel transported tetrad frame, a scalar component of the full curvature tensor or its covariant derivatives is diverging. This is another way of saying that a tensorial part of the Riemann curvature tensor is divergent. And I just chose here a parallel transported tetrad frame because in such a tetrad frame, each component function of a tensor is a scalar, right? And so that's important because remember that if the component functions are not scalar, then you can change them by change of coordinates. And so whether or not they are big or small may depend on your choice of coordinate system. But if you decouple the choice of bases in your tensor space from the choice of coordinate system, then you can look at the true size of those components. They're no longer dependent on the coordinate system. In this case, when we have a divergence in the scalar component functions of a tensor in a tetrad frame, then we say that parallel propagated curvature is singular. It could also be none of the above. In fact, it could have nothing to do with curvature and still be non-trivial. And to see how that could come about, let me just take a piece of paper and imagine I roll this up so that it becomes like an ice cream cone, right? This is not very strong paper here. Okay, ice cream cone, okay? You all know how that looks like. The surface of the ice cream cone is actually flat. There's no particular curvature going on the surface of an ice cream cone. But what about the tip of it? At the tip, curvature is not even defined. And a space-time can have that kind of singularity as well. For example, you could take a plane, cut out a piece of, like a slice of pizza, cut it out, and then identify at equal distance from the origin those points, and then you have basically an ice cream cone. And at the center, you then have a singularity. It's called a conical singularity instead of a curvature singularity. And those, in principle, have to be taken seriously as well. Now, here's the fundamental problem that we want to address. In concrete solutions, such as the Schwarzschild solution for black holes or Friedmann-Lemaitre cosmologies, curvature singularities are obviously present. If you calculate the curvature scalar in those cases, then you see that they blow up at the singularity, at the center of the black hole, or at the Big Bang. But these spacetimes are highly symmetric. And the question is, as we started off this lecture today, in a more realistic case where we have perturbed spacetimes, do we also have those singularities? Or are they perhaps resolved? Just like the figure skater, you know, when she pulls in her arms while rotating, she will spin faster and faster. And so when you have gravitational collapse, in principle, the spinning could just go so fast that eventually it makes stuff fly apart again, which is what would happen classically. But in Einstein gravity, this doesn't seem to happen. By the way, I find it curious that nature has found two completely different ways of stabilizing collapse. So here in gravity, gravitational collapse, in principle, if it weren't for general relativity, according to Newton, gravitational collapse could be disastrous for all of the universe in principle. If one star were to collapse without stopping, then you see the potential well in principle, if 1 over r, is infinitely deep. And you could have that it all collapses, goes deeper and deeper into this negative energy hole, while emitting energy out there unlimitedly, right? So there could be an unlimited amount of radiation that could come from one stellar collapse. And that would make the universe unstable. General relativity stabilizes gravity in that a black hole forms, the gravitational collapse comes to a stop, a black hole forms, and that black hole is the lowest energy state then, and it will not on its own get any more contracted. It will not on its own get into a deeper potential well. A similar situation, in principle, arises with a proton and an electron forming a hydrogen atom. If it were up to classical physics, then, or let's just say a positron and an electron, because the positron is point-like, in principle, they could spin closer and closer to each other, sink deeper and deeper into a potential well of 1/r type, and therefore, while the electron and the positron spin closer and closer together, without bound, they could radiate off an infinite amount of energy. And again, the universe would be unstable. In that case, it's quantum theory, and it's the uncertainty principle that saves us. The uncertainty principle means that if you make the delta x of an electron small enough, the delta p starts growing. But that means that the electron, as it gets close to the positron, cannot be slow. It has to be fast, and that allows it to escape, and you get the smallest Bohr orbit, and that is what stabilizes matter. So quantum theory. And so black holes and the uncertainty principle perform sort of the same task. They stabilize 1/r potentials. Now, of course, in GR, it's not exactly 1/r, but it's still, in principle, going down like that. If it went for black holes, it would be an instability. Okay, but we're still to prove that singularities really ought to appear in general relativity. Is that really a robust prediction? It turns out that it is a very robust prediction, and quantum gravity will then have to resolve those singularities. It will have to overcome that robustness. If quantum gravity is to cure those singularities, the breakdown of the theory itself, then it will have to get around this. So here's the strategy for proving singularity theorems. I think all or almost all singularity theorems are proven with this strategy. First, we focus attention on singularities that can be identified by the existence of incomplete, inextendable geodesics that are time-like or perhaps null. Now, it's clear that these are important singularities because you could personally run into one of those, because you can travel on time-like and space-like geodesic, time-like and null, or maybe not null geodesic, but time-like ones. On the other hand, there could also be space-like paths, space-like geodesics that identify singularities, but we don't know of any relevant cases yet. So what it would mean for a traveler to find such a time-like singularity is that for a traveler, time comes to an end at a finite eigentime, right? So the traveler watches his or her clock and travels and eventually hits a singularity at a finite eigentime. And so it's the end of the world for that person, literally. Okay, so point A was we focus attention on the time-like and perhaps null geodesics, and the time-like and null singularities. The basic idea then for identifying those singularities is that they can be in the way of these geodesics, and that interferes with the property of geodesics of being of extremal length, curves of extremal length. Remember, extremizing curve length gives you the geodesic equation. It's the Euler-Lagrange equation for the extremization of the length. And the geodesic equation is a differential equation. So at least locally, geodesics are paths of extremal length. Space-like geodesics are curves of shortest proper distance, as you might expect on a curved surface. The geodesic distance between 2 points is the shortest distance between those 2 points. But notice that time-like geodesics are curves of maximal proper time, not minimal proper time. So for example, if you throw a stone from one place to another, then the path that it takes is going to be a path of maximum eigentime, maximum proper time for the stone. How do you see that it's maximum and can't be the minimum? Well, imagine that this stone has a rocket engine in it. And you arrange that it has the same starting time and the same arrival time than a freely falling rock. But let's say you have 2 rocks. One is just freely falling, and the other one has a rocket engine attached to it. And the one is just flying, freely falling from point A to point B. The other one goes on a huge trip, very fast, but comes back in time so that it hits the arrival point the same time that the other one was, the freely falling one is arriving there. Well, the one that went on a huge trip was much faster. And you know, when it's traveling faster, then its proper time passes slower, right? So it's less eigentime. So time-like geodesics are actually curves of maximal proper time. And the compromise between speed, slowing down the clock, and gravity, speeding it up, that is what gives you the actual parabolic shape of the curve. Okay, and then we prove that even in a generic space-time, there always exist curves of maximal length between 2 events. Now, what assumptions are needed for a singularity theorem? Well, usually a key assumption is that the space-time is globally hyperbolic, which in particular is excluding closed time-like curves and so on. Right? Because we have a global time function, if you remember. Then point E, further we have to assume that matter obeys a suitable energy condition. Now remember, we had the weak energy condition, which said that the energy density ought to be positive for a co-moving observer. The T0 component of the energy momentum tensor ought to be positive. We had the dominant energy condition. Dominant energy condition is the weak energy condition plus the statement that the flow of the energy, even though it might not be conserved, has to be on or inside the light cone. And unfortunately, neither of the two is usually good enough for a singularity theorem. And you have to assume the so-called strong energy condition. And the strong energy condition doesn't really have a very nice interpretation in terms of energy. And that's because really what we have to impose is a condition on the Ricci tensor, where it makes sense, the condition. And then using the Einstein equation, we translate that into a condition on the energy momentum tensor, as you will see in a moment. So on the basis then of such a energy condition, our aim then is to prove that geodesics meet a divergence of a quantity called the expansion, theta, in a finite proper time. So we want to show that, I mean, this is not for conical singularities, but for curvature singularities. So we will be concerned with singularity theorems to prove the unavoidability of curvature singularities. And we do it by showing that geodesics necessarily, under certain conditions, geodesics will necessarily come to an end at a finite proper time. So you travel on a time like geodesic, at a finite proper time, the geodesic comes to an end because a quantity called the expansion, which is literally the expansion of space-time, or compression of it, will diverge. So we have a curvature singularity there. And that in itself already proves that these geodesics cannot be extended because the space-time itself would not be defined where that curvature is infinite. So we'd like then to conclude that there are incomplete geodesics and therefore that we have a singularity in the past or in the future. A singularity in the past is of interest for cosmology. Was there a Big Bang? Singularity in the future is of interest, for example, if you are navigating between black holes. So concretely, here is a singularity theorem. There are several, and we don't have time for all of them. Let's just look at one of them more closely. So let's assume that the space-time is globally hyperbolic, so it has Cauchy surfaces. The energy-momentum tensor of matter is going to be a cosmological singularity theorem. Now, so we assume that space-time is globally hyperbolic. We assume that the energy-momentum tensor obeys the so-called strong energy condition. The strong energy condition is that this combination here of the energy-momentum tensor is larger or equal to 0 for all time like xi. And there is not really any good interpretation for what that condition means in terms of energy and momentum. And the reason is that we'll need that condition for technical reasons arising as a condition on curvature. You see, if you remember, the Einstein equation in 3 + 1 dimensions can be rewritten equivalently in a slightly different form. Namely, you can probably not read that. The Einstein equation can be written in this form. This expression here that is in the bracket is equal to the Ricci tensor. Right? So the Einstein equation can also be written in the form of this equal to some gravitational constants times the Ricci tensor. So really what this is a statement on the Ricci tensor. It says that when you contract the Ricci tensor with a time-like vector, then you get an expression that's larger or equal to 0. But it is a condition that can be checked. So you assume that the universe is filled with some perfect fluid, or you assume that it's filled with some kind of quantum field, or whatever it might be. Then you can calculate the energy momentum tensor, and you can check whether the condition is obeyed. Okay, so that's one condition. And another assumption is that there exists a twice continuously differentiable space-like Cauchy surface sigma, on which the trace of the extrinsic curvature is bounded from above by a negative constant. Now, we didn't really go into the extrinsic curvature. I'll say a little bit more about it later on. We can express that in terms of the expansion that I talked earlier, and we will do that in great detail. Yep.
So is there any intuition for this condition, that the Ricci scalar,
this one?
Ricci tensor contracted, but the two vectors give?
No, unfortunately, it comes up purely technically. We will end up with an inequality, and there is one offending term of which we don't know whether it's positive or negative. And in order to go further with the proof of the existence of a singularity, we have to assume that this offending term is positive, and that is the offending term. That's how it works. You will see exactly how it comes up. Yes?
Is the extrinsic curvature the mean curvature?
The extrinsic curvature is the curvature between the Cauchy surface, and which is a 3-dimensional manifold, space-like hypersurface, and the 3 + 1 dimensional manifold in which it is embedded. It is, intuitively speaking, the curvature between space and time. And if you remember, the curvature between space and time is expansion or contraction. And so we will later reformulate that in terms of the actual expansion. Remember in Friedman, Robertson, Lemaitre, Walker spacetimes, we have the scale factor, which is a global function that globally describes how the spacetime is expanding. we'll have to make that local. We look at the local expansion, local shrinkage of the space-time.
So this strong energy condition, like even when checking it for, let's say, models like perfect fluid or quantum fluctuations, we still don't see what does the
Well, there you may have a chance that it comes up naturally. I don't know of a case where it would be where the natural interpretation jumps out. But of course, it would be nice, right? Could be that you have some model of what fills the universe, and then there is a parameter with an obvious interpretation, which if you tune it this way or that way, you get positive or negative, right? And also remember that quantum fields can basically break all of the energy conditions. So everything is possible there. Okay, so we will make an assumption here on the extrinsic curvature, which is basically to say, let's assume, and that's how we will use it, let's assume that the universe is currently expanding at a rate that is not below a certain amount everywhere. And then, using the energy condition, running the evolution backwards, even if we can't solve it analytically, we can prove that it must have started in a singularity. Right? So if you know at what rate it is expanding now, running it backwards, you get a contraction, and with the energy conditions, you then prove that it must have it must have started with a singularity. And similarly for a black hole, of course, you go forward then. And also for black holes, you actually need an additional concept, that of a trapped surface. And we will get to that towards the end today. Okay, so with these conditions, with the conditions of what's the status of the contraction or expansion at the moment, and energy conditions, and assuming that the space-time is globally hyperbolic, we can then conclude that in the case of cosmology now, no path-directed time-like curve from our present-day space-like hypersurface can have an eigentime that is a proper length larger than 3 over c, where c is the constant that bounded the expansion rate. In other words, given the energy conditions, given the Hubble parameter now, the rate of expansion now, even if it's not in a symmetric case, if you can put a bound on the expansion now, a bound c, then you can tell that the universe cannot be older than such and such. Because there is no path-directed time-like curve whose proper length is longer than that. So you can put a bound on how old the universe might maximally be. So in other words, we are proving that all path-directed time-like geodesics are incomplete. And so there is a cosmological singularity in the finite past, which is where those path-directed time-like geodesics end. So what again was the extrinsic curvature? Well, the extrinsic curvature of a space-like hypersurface describes how much curvature there is between the space-like hypersurface and the time dimension. I think I said all of these things already. And intuitively, it is the rate of the expansion of space-time locally. Expansion or the rate of contraction. So the assumption that this extrinsic curvature is smaller than a certain constant is to say that space-time has a finite minimum expansion rate everywhere on a space-like hypersurface such as today. But we will later define the expansion explicitly in great detail. What again was this strong energy condition? Let me just quickly remind you, the weak energy condition that we had earlier is simply saying that this is larger or equal to 0 for all time-like vectors, and if you're co-moving with this time-like vector, then it has only a 0 component. So the vector v is, in the rest frame of v, it's just v naught, 0, 0, 0, 0, and therefore this is just saying that t naught naught is larger or equal to 0, the energy density is positive. The dominant energy condition is the weak energy condition plus the statement that this vector, which is describing sort of the flow of the energy, even though that's not completely true because the energy is not, and this 4 vector is not a conserved quantity, but in any case, we're requiring that this 4 vector of the flow of the energy is on or in, pointing on or into the light cone, so that energy is flowing causally. Now, the strong energy condition is, as we said already, this condition here, and what it does is this condition prevents a term from interfering with the expansion. Remember, the singularity theorem says that if you assume that the universe is expanding now everywhere at a certain minimum rate, that doesn't have to be the same everywhere, but it has to be bounded from below everywhere, then you can run things backwards in time and you find that there must have been a singularity in the past. If that condition was not obeyed, then you cannot draw that conclusion, which is to say that there could have been, the energy momentum tensor might be such as to prevent this. And you can think of it as matter that would interfere with the usual expansion and contraction. And that's basically like dark energy that would cause a matter that would actually accelerate the expansion instead of slowing it down. Remember that dark energy has a negative pressure. So it's not exactly true to say that this is excluding negative pressure, but I'll show you in a moment in more detail what it says. Okay, so it's actually a condition that's independent of either the weak or the dominant energy condition. And here is the relationship. For known matter, the energy momentum tensor is diagonalizable, and we have energy density and pressures. They're called the principal pressures. And the 3 energy conditions then are the following. The weak energy condition is that rho itself is positive, and that rho plus the principal pressures is also positive. Plus each individual of those principal pressures is positive. The dominant energy condition is a little bit more restrictive. You see, this equation you can read as rho is larger or equal to minus pi, right? Rho is larger or equal minus pi. But the pressure can be positive or negative. This dominant energy condition says that rho is larger or equal to the absolute value of pi, which is always positive, and therefore it's slightly more stringent than that. The strong energy condition says that rho is larger or equal to the sum of the principal pressures, larger or equal to the negative of the sum of the principal pressures. Right. Right, and I've put here some comments for what would happen if you had a cosmological constant in the energy momentum tensor. Look at it, work it out yourself, play a little bit with those energy conditions. So basically, the exercise is show that the strong energy condition is violated in cosmology if W is smaller than minus a third, which is to say that if the expansion is accelerating. That is for an FRW space-time. If the space-time isn't fully symmetric, like an FRW, then you can't really say, you can't really interpret these things as easily. All right. Remember, what we are aiming at in order to prove the existence of singularities is that the so-called expansion, the local scale factor, is exploding. You see, we can only work with the local quantities because we are no longer assuming FRW spacetimes. We are no longer having a global scale factor. We only have local scale factors. But how do we define local scale factors? How do we define the expansion locally? This is quite non-trivial because curvature there's more to curvature than just expansion or shrinkage. Curvature also has, rotation. Curvature also has shearing. So we should expect that in a generic space-time, it's a much more complicated thing than just saying we have expansion or shrinkage. But there will be expansion and shrinkage, and that's the part that we will be focusing on to get at singularities, but it's a more rich structure. So how do we define then the expansion as a local expansion or local shrinkage of a space-time? So here's how that goes. How are we doing with the time? Okay. Okay, so the expansion. For this purpose, we need to, it might look like what we're doing now is going to be rather specialized. We want to prove singularity theorems. But actually, the tools that we will need for proving the singularity theorem will be all-purpose tools that come up all over the place. So I hope you appreciate these things. For example, even if you want to go into the study of supernovae, then stellar collapse, then you need the Raychaudhuri equation, which we will also need here. And so that we're going to go in quite some detail, but not only for the purpose of the singularity theorem. We'll see a lot of useful things. Okay, so let us introduce the concept of the congruence of time-like geodesics through some space-like hypersurface sigma. What we mean by that is this. Imagine we are all astronauts, and we are in full gear, and we are placed out there in empty space, and we are floating. And we are just sitting there, let's say, everyone is at 1 meter's distance from everybody else, maybe holding hands so that we are not drifting apart. Okay? And then everybody has a synchronized watch on their wrist. And when that clock strikes 12 o'clock, then we let go, and we just start freely floating. What would we expect? Well, if it was just the Friedmann-Robertson-Walker space-time, we would expect to slowly drift apart. You really have to have some patience to see it. But that's what we would expect, right? But in general, in a general space-time, not assuming any symmetries, we would be performing some intricate dance, right? Because in general, we might be drifting apart. Some of us might drift closer. Some of us might drift around each other, All that stuff might happen. And that's what we study with the congruence of time-like geodesics. The moment we let go, we are going to be on time-like geodesics. And a congruence of time-like geodesics is a family of time-like geodesics. So a congruence of time-like geodesics is a smooth family. So smooth is a differentiably parameterized family of time-like geodesics, where exactly one geodesic goes through each point of our space-like hypersurface. So the space-like hypersurface could be now, right? So the 12 o'clock, that is the space-like hypersurface. When it's 12 o'clock on all those wristwatches, then these events, the 12 o'clock events, assuming that there's an astronaut everywhere in the universe, that is a space-like hypersurface, and each astronaut is describing a time-like geodesic then. And a geodesic is parameterized by proper time, namely our wristwatches, and also there's going to be a parameter that parameterizes us relative to each other. So first of all, the time direction for us is d by d tau, where tau is the wristwatch time. And so there is a time-like vector field psi which is tangent to each one of us. Right? So each one of us has a time-like geodesic, and the tangents to all of our time-like geodesics are describing a time-like vector field psi, which is d by d tau, where tau is our wristwatch time. Okay, so that's that. And properly normalized, it has length -1, length squared -1. Now, let us consider a line of us. So we should really be arranged in a 3D structure, but let's just say we're looking at a line of those astronauts. And along that line, there's a parameter running that we might call S. Okay, S equals 0 is me, S equals 1 is you, and so on. S equals 2 is Keith, and so on. Right? So we have now, this is us, this is some of us astronauts there, and psi is the tangent to each of our geodesics, and S is the parameter that labels the astronauts, and eta is the space-like direction vector that points from astronaut to astronaut. So we have time-like geodesics this way, and we have space-like geodesics that way. And the tangents to those space-like geodesics that way are d by ds, and the vector field, this direction, is d by ds, is eta. We call it eta. So psi upwards, eta in the space direction. And then the key question is, if we want to know what our ballet is doing, we need to find out what eta does as we progress in time. So the vector eta is pointing from one astronaut to the neighboring astronaut. And we want to know, as we move up in time, how does this eta vector that points from astronaut 1 to astronaut 2, how does this eta vector change? For example, if the vector lengthens, it means those two astronauts are drifting apart. If the vector shortens, the astronauts are getting closer to each other. If the vector rotates, well, then we're going to be in a spin around each other. Okay, so how does eta change along a geodesic? Now, tau and S are actually Riemann normal coordinates for geodesic traveler. For this fellow here, or any fellow, right? The parameters S and T are parameters of geodesics, and therefore at the origin of a Riemann normal coordinate system, it's clear that, I mean, these are two of the coordinates in a Riemann normal coordinate system, and so they are just commuting with each other. So we have that in an arbitrary coordinate system where d by ds is eta and d by d tau is psi, we have that the two vector fields commute. Now, how does that relate to covariant derivatives? Remember that in general relativity, the torsion is vanishing. So we have 0 equal to the torsion, but the torsion map is the commutator of the covariant derivatives minus the commutator of the fields. And the commutator of the two fields psi and eta is vanishing, as we just established. So what we have is that this condition holds true, that this is equal to 0. So we conclude that for those two vector fields psi and eta, this condition holds. Let's spell out what that is explicitly. So this is the covariant derivative of eta in the direction of psi. Psi can be expanded as psi mu e mu, and the psi mu coefficients can be pulled in front. So we have this, and the same operation on the right-hand side. And these are the coefficient functions that we get from the covariant derivative, if you remember. And finally, we obtain that psi mu, eta nu, semicolon mu, equal to this expression. And what this is saying is that along the geodesic direction psi, so as we progress in time, the spatial deviation vector eta, the vector that points from astronaut to astronaut, changes its direction and length by a certain matrix here. You see, what is this? This is the covariant derivative of eta in the direction of psi. See that? We have the eta vector, eta nu. If we want to covariantly differentiate it in the direction of psi, then we have to write a semicolon mu contracted with the direction vector psi. So we calculated here the covariant derivative of eta in the direction of psi, so forward in time. So in other words, we calculated how, if you're pointing to your astronaut neighbor, then how your pointing vector is changing as you move along your geodesic. And we obtained that it is this expression, which is this matrix contracted with the eta vector, which is to say that the covariant derivative of the eta vector is given by the eta vector contracted with this matrix B. B for ballet of the astronaut. Okay, so now we want to know, is this eta vector, the vector that points from astronaut to astronaut, is it changing its length? Is it getting longer? Are the astronauts going to drift apart? Is it getting shorter? Are the astronauts going to drift towards each other? Are they going to dance around another? And so on. Well, so we have to analyze this ballet vector B. It can be decomposed covariantly and uniquely in the following way. I mean, remember, it's really just a tensor, right? It's a one-fold contravariant, one-fold covariant tensor. Let's pull both indices down and then decompose it. We can decompose it into an antisymmetric matrix plus a symmetric matrix. You can always do that. You can always decompose a matrix into an antisymmetric part and a symmetric part. Now, the antisymmetric part doesn't have a trace. The symmetric part has all of the trace. I mean, the antisymmetric part has a trace, but it's zero. The symmetric part can have a non-zero trace. Let's decompose that into a part that has no trace, sigma, and a part that is the rest, which has its symmetric part with a trace. And this decomposition makes sense because these are the three possible ballet moves that two neighboring astronauts can do. Now, first of all, the antisymmetric part is by definition, of course, just that, antisymmetrized. What are the sigma mu nu and t mu nu? Well, in preparation for defining the sigma mu nu and the t mu nu, we need a projector. We need a projector onto the space that's orthogonal to the time-like direction. Psi is the time-like direction. It's the direction of our geodesics. And h mu nu is to be the projector onto the directions orthogonal to the time direction. So just onto the spatial components. And that is the projector. H mu nu is g mu nu plus psi nu. This tensor will project onto just the space-like directions, orthogonal to psi. Let's check that. Let's say W is an arbitrary 4-vector. And we applied this supposed projector on it. So we take this tensor here and contract it with this arbitrary 4-vector. We want to know whether the result is really orthogonal to psi. Because that's what we are supposed to do. I mean, this is what this H is supposed to do. It's supposed to project onto the space orthogonal to psi. Okay, let's check. So we take this vector, that is hopefully orthogonal to psi, and contract it with psi and see whether we get 0. So we get psi, this projector, and then W. But that is, by this definition, we have psi g mu nu W, that's psi W, and we get psi W. So psi is -1 and psi W, so indeed these things cancel and it's 0. So that's the projector. Now we can define the expansion that we've been looking after. This is the thing that, as we will see, describes how much astronauts will drift apart from each other or drift towards each other. So the expansion is defined to be the magnitude of the spatial part of this Belay matrix. So you take the Belay matrix B mu nu and contract it with the projector. So that gives us the B matrix, but only in the spatial directions. And that's a scale. It's a scalar because we're contracting both mu and nu. And that is, by definition, theta. That's the claim that this is also just a trace of B. So that's the definition. The definition is that theta is the projection of B with H. And the claim is that this theta is also simply the trace of the Belay matrix. And here's the proof of it. It's straightforward. So therefore, what we obtain is that the sigma mu nu matrix, if you remember, that's the matrix which is symmetric and traceless. Let me remind you. Okay, here's the Belay matrix. And it has an antisymmetric part. It has a symmetric and traceless part. That's the part that we want to calculate now. And it has the remainder. So we can now identify the symmetric and traceless part. The symmetric and traceless part of the Belay matrix is the symmetric part of the Belay matrix minus a third of the of theta times h mu nu. Again, easy to check. And we can then also identify what the remaining term is in this decomposition of the Belay matrix into 3 terms. The term that actually has a trace in it, a non-zero trace. That's the term. T mu nu is 1/3 theta h mu nu. Notice the expansion. What we will find is that in the Belay matrix, the third term, the symmetric term with a trace, that's the one that describes the expansion. Here's the interpretation in more detail. Omega mu nu is the antisymmetric part of the Belay matrix, right? So we want to understand now what is the role, what are the dance moves of those 3 terms here in the Belay matrix. Let's start with the omega mu nu. Omega mu nu is antisymmetric, okay, by construction, which means it generates Lorentz transformations. If you remember, the antisymmetric covariant 2 tensors generate Lorentz transformations for the eta, right? Because remember, eta changes by the application of the Belay matrix on eta. So we have to apply this omega on eta, and that means we apply a Lorentz transformation on eta. But all the eta are orthogonal to the time direction, which means that all this does is that it generates spatial rotations. In other words, that means that the two astronauts exposed to such an omega are doing it what is called a twist. So but really they're just rotating about each other. A Lorentz transformation that doesn't have a boost in it is just a rotation. So the omega mu nu contributes to a rotation of astronauts around each other. Now it turns out that if you choose your congruence of astronauts, if you choose your congruence of geodesics in such a way that they start orthogonal to the space-like hypersurface, then actually that rotation is vanishing. So in other words, if we are, as astronauts out there in space, and as the clock strikes 12, we let go, and we started out being at rest relative to our space-like hypersurface that we chose. then we are not going to start rotating around each other. It's not going to happen. If, however, we started out already in motion relative, if we had a velocity relative to the space-like hypersurface that defined equal time, then it's possible that we start rotating about each other. It's a non-trivial proof, though, so it's too long to cover here. Now, let's look at the second term in a decomposition of the Ballet matrix. The second term is symmetric. Okay, so sigma mu nu is sigma nu mu, which is to say that it's symmetric but traceless, right? And because it's symmetric, you can view it as a Hermitian matrix. It's only the spatial components really matter, so it's really Hermitian, really self-adjoint, and you can diagonalize it, and by suitable choice of bases. And that means that the sigma mu nu is changing the length of the basis vectors according to the eigenvalues of sigma mu nu. So that means that in some directions, the distance to the neighbors might be increasing. In some directions, the distance to the neighbors might be decreasing. The eigenvalues could be positive and could be negative. And the trace is actually 0, which means that, yes, there will be positive, but then they have to be offset by also negative eigenvalues. What that means is that if, for example, our astronauts are starting out forming a sphere, then as time passes, that sphere will be squeezed and stretched. In some directions, the sphere will be expanded, but it will be offset by a contraction in another direction. The sphere will become an ellipsoid. And I'm putting that just to say that tracelessness means that it's exactly keeping it in such a way that the volume spanned by those vectors stays the same under the action of the sigma. Right? Because the determinant of the exponentiation of the sigma matrix is going to be 1. Because the trace of the sigma matrix is 0, the exponentiation of that has a determinant of 1. Because any stretching in one direction has to be offset by a compression in another direction, what this tensor is doing is a shear. It's not making a sphere any larger overall or shrinking it overall, it's just shearing it, right? So the sigma mu nu is also called the shear tensor. So the omega mu nu was the twist, it's a rotation. The sigma mu nu is a shear. What is the third term? Now, the third term is the expansion. The third term, T mu nu, is a third times this scalar function theta here, which, if you remember, is the trace of the Ballet matrix, times h mu nu, which is the projector onto just the spatial part. So what we see is that this tensor is actually generating an expansion or shrinkage. If the astronauts are arranged in a sphere, that sphere will shrink or grow depending on the size of theta, on the size of that trace. So what we will be interested in is the evolution of that theta, of that growth or shrinkage parameter, which, if remember, it depends on space and time, right? This is not like in FRW, just the overall scale factor. No. This is the rate of change of the expansion or shrinkage of the universe. Concretely, it is how quickly parallel geodesics move apart from each other or move closer to each other. And what we will study is under which circumstances there can be a divergence of that quantity theta. If that is divergent, then the geodesics cannot continue beyond that, and we've hit a singularity, either in the future or in the past. Okay, but in our intermediate in our immediate future should be a break. All right. Okay. See you then in like 20 minutes.